Savino and Barnes, injury attorneys, 800-888-8888.
Don't wait, call 8.
In the first video, we gave a careful definition of what it means to be a tensor product of two R modules, and we showed that a tensor product has to satisfy a certain kind of uniqueness. In this video, we're going to prove that a tensor product of two R modules exists. So I'll be a little careful. I'm not going to give a fully detailed proof here because this is not the kind of proof that you would be expected to reproduce on an exam. And I find that it's more important to emphasize things you can do with tensor products and examples rather than their actual construction, which you don't end up coming back to very often, at least in this course. So here's the idea. Let's consider M cross N as a set. So we have these R modules M and N, and we want to show that a tensor product of these R modules actually exists. So we start with M cross N, and we're going to take the free R module on the set M cross N. So we'll denote this FR sub R to emphasize that it's an R module on M cross N. What does that look like? This has one coordinate for each element of M cross N. So you can think of it as like a very long string where you have a coordinate corresponding to the first element of M cross N, another coordinate corresponding to the next element, and so on, and so on, and so on, and so on. And we're going to let delta M comma N be the element in this free R module that is 1 in the coordinate corresponding to M comma N and 0 everywhere else. So I want to point out this is really, really similar to the argument in the proof of theorem 6 in section 10.3 of Dummett and Foote. This is a proof that I only sketched but didn't do in detail in lecture. So in that setup, M cross N is playing the role of A. This little a is like this element, M comma N. And what Dummett and Foote call F sub A is delta Mn here. So this construction of this free module should be familiar from theorem 6 that we talked about in the last lecture. All right, so then what is this free R module? It's this giant direct sum taken over all of the elements in M cross N. So all the elements of R times this delta M comma N. So I just want to emphasize this is a really huge free module. This has one coordinate for each element in M cross N, not just one coordinate for each standard basis vector. Like if you take the free R module of rank N, what does it look like? Elements look like vectors of length n, a1 up through an, where ai is in R, but there's n coordinates, 1 for each standard basis vector, 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on. So here, this thing might be infinite, but it only has n coordinates. Here, in this free R module, you really have one coordinate for each element of M cross N. So this is this gigantic thing that's kind of hard to get your hands on. All right, why are we looking at this thing? Because the tensor product is going to be constructed as a quotient of this giant free module. So what are we going to take the quotient by? Well, let's pause and erase, and then I'll tell you. We've been talking about this huge free module on the elements of M cross N. And we're going to construct the tensor product as a quotient. A quotient by what? Let's say that D is the submodule of this free module spanned by all of the elements of the following form. Delta M plus M prime comma N minus delta M comma N minus delta M prime comma N. Okay? Delta M comma N plus N prime minus delta M N minus delta M N prime, delta R times M N minus R times delta M N, delta M R times N minus R times delta M N, and then delta R times M comma N minus delta M times M comma R times N. Okay, so that's the kind of thing where it's most helpful to just look at these relations. I'll say in a second why these particular elements are the ones that we're taking as a spanning set for this submodule D. But now we're going to define M tensor N to be the quotient of this free module by D. Okay, so that's our definition. You certainly can take this quotient. Now we just have to show that there is a nice bilinear map from M cross N to this R module, and that this R module satisfies the universal mapping property of the tensor product. So we'll focus on the first part for now. So for one thing, what does an element in this quotient look like? Well, it's a coset of this submodule D in this free module, which is this giant direct sum involving these elements delta Mn. So we're going to write the coset delta Mn plus D in this tensor product as M tensor N. All right. Now, from the definition of D, we get a bunch of relations in this quotient. What does that mean? Well, which things are in D itself, things that are in the span of all of these elements. So when are two things in the same coset of D when their difference actually lies in D? So for example, delta M plus M prime comma N is equivalent to delta Mn plus delta M prime N mod D, meaning that these, the element on the left and the element on the right, are in the same coset of this submodule D. But if we write these cosets with this tensor notation, this is exactly the same thing as saying that M plus M prime tensor N is equal to M tensor N plus M prime tensor N in this tensor product. All right, so these elements, these M tensor N elements, satisfy a kind of distributive property. And if you go through the other kinds of elements that are used in defining D, you see other relations that have to be satisfied by these tensors. M tensor N plus N prime is M tensor N plus M tensor N prime. R times M tensor N is the same thing as M tensor R times N, which is the same thing as R times M tensor N. So why is D defined the way that it is? It's defined this way in order to force this map from M cross N to this quotient, the free module on M cross N mod D, that takes the pair M comma N to this M tensor N to be a bilinear map. So these relations are exactly the relations that are needed to see that if you hold one coordinate constant, you get an R linear you get an R linear map, you get an R module homomorphism from M to this free module. Same thing if you hold M constant, you get an R module homomorphism from N to this. So you can check, and you really should check once, that this map really is bilinear because of all these relations that are satisfied. So what have we seen? We've seen that starting with an R module M and an R module N, we have this R module M tensor N defined as this quotient of this giant free module by the submodule D generated by these collection of elements. And we have this very nice bilinear map from M cross N to this R module, M tensor N. So in order to show that this really satisfies the definition of a tensor product, we now need to see that there's a correspondence between bilinear maps from M cross N to some R module P, and then R module homomorphisms are linear maps from the tensor product to that same R module P. So before we get into that, I just want to say, okay, we've seen one nice bilinear map from M cross N to this tensor product. You might want to ask, like, well, what about others? Like, this isn't the only bilinear map we could have come up with, but this is the only one that we're going to deal with in showing that this tensor product really does satisfy the definitions necessary that were given at the beginning of this lecture. So we've seen that the tensor product is this R module and we have this nice bilinear map from M cross N to M tensor N. So what do we need to know now? We need to know that all bilinear maps out of M cross N factor uniquely through the map M cross N tensor goes to M tensor N. All right, so what does that really mean concretely? Let's take a bilinear map from M cross N to P. Let's call it B. And now the idea is we're going to use the universal mapping property satisfied by free modules in order to understand maps out of the tensor product. So the universal mapping property for free modules gives a unique linear map L from this free module on M cross N to P such that L applied to delta M comma N equals BMN for all pairs M comma N in the direct product. And so that this diagram where you could start over here at M cross N, apply B and go down to P, or you could apply this inclusion of M cross N into the free module where you take the pair M comma N to delta MN and then apply this linear map L commutes. So, okay, saying this again, the universal mapping property for free modules guarantees that there is this unique linear map L from the free module down to P such that you apply L to delta MN and you get BMN, that is, this diagram commutes. Where did that come from? Well, this is exactly what is stated in theorem 6 of section 10.3 from last time. If you apply this theorem with A equals M cross N, and unfortunately the notation's a little overloaded, the M in the statement of that theorem should be P, and this map of sets from A to P, in this case, well, A is M cross N. Oh yeah, this is to M, which is P in our case. So it's this map from M cross N to P. We only have one good choice, which is B. And theorem 6 gives you the existence of this unique linear map that makes this diagram commute. Okay, so what are we going to do with this linear map that comes from this universal mapping property for free modules? For one thing, we don't want a linear map out of a free module. We want a linear map out of the tensor product, which is this quotient by D. So what we have to do, and here is the part where I'm not going to write in all the details, but I'll give you a sketch of what the major steps are. So we have to show that this map L makes sense, not just as a function on this free module, but as a function on the tensor product, which is this free module quotiented by D. What does that mean, makes sense? Well, this is going to give a well-defined map on this quotient if D is contained in the kernel of this map L. So that's what we need. We need to show that D is contained in the kernel, which means we need to show that the kernel contains all of the generators of D. So if all of the generators of D are sent to 0, then all of D will be in the kernel. All right, so once we do that, we want to show that now not only do we have this map L that goes from the free module, but we get a map capital L that goes from the tensor product down to P. And we need to show that it satisfies the definition necessary to be a tensor product, this definition 3.1, that this map L from M tensor N to P is the unique one that makes this diagram commute. You start at M cross N, you apply B, you end up in P, or you go around the other way, you take the tensor, you end up with an element M tensor N, then you apply this L. All right, so I'll pause and erase. I'm not going to do all of the details here. You can find them in Conrad's notes, but I am going to give you some idea of what goes into proving this statement. Let's finish up this discussion of the existence of the tensor product. We use the universal mapping property for free modules to get a linear map from our free module down to P. And then we have to show some things about how this map behaves at the generators of this special submodule D to show that that gives a linear map from the tensor product to P. And now we want to show that this linear map that we got is the unique one that makes this diagram commute. Okay. What do we need to use here? We're going to use the uniqueness of the elements of our free module as finite R linear combinations of these delta mn to see that elements of the form M tensor n span the tensor product as an R module. Right? We have this map that takes pairs M cross n into this tensor product, but we don't know anything about the image of this map, really. I mean, we know that for every pair mn, we have this M tensor n, but that's not everything that's in this tensor product up here necessarily. So we have to show that elements of the form M tensor n span this R module. So I'm putting this in a box because this observation is going to be useful even outside of this proof that a tensor product exists. And then, because this is a spanning set, if you have a linear map, an R module homomorphism from the tensor product to P, it's completely determined by what it does to a spanning set. So it's completely determined by what it does to these elements M tensor n. Well, we have found one linear map L that satisfies L applied to M tensor n is equal to this bilinear map BMN. And this is a linear map. There's no other different linear map that takes the same value at every element of this special spanning set that we have. So this L is the unique linear map so that L applied to M tensor n is always equal to BMN, and this diagram commutes. So that shows that our tensor product together with this special bilinear map from M cross n into the tensor product really does satisfy the definition of a tensor product. So what I really should say is that this quotient of this free module, free R module on the set M cross n, mod out by the submodule D, which we described explicitly in terms of generators, that this R module together with this tensor map satisfies definition 3.1. And because tensor products satisfy this very strong kind of uniqueness that we talked about earlier, we can just say that this is the tensor product of M and n rather than a tensor product of M and n.